this video, we're going to consider the second type of improper integral. And the second type of integral that is considered quote-unquote improper is the case that either the upper limit of integration or the lower limit of integration, or perhaps both, corresponds to a vertical asymptote of the function that you're trying to integrate. So let's get a nice sketch going here. Here is the graph of the function 1 over square root of x. As x approaches 0, we're dividing by 0, giving us an infinite output. And so on the interval from 1 to 0, this function looks like this. It has a vertical asymptote, VA for short, at x equals 0. So the question is, what is the area under this curve as we get closer and closer to 0? Is the area infinite? Is it finite? What number is it if it is finite? Let's figure that out. Now, again, this process begins the usual way. For a definite integral, we begin by rewriting this integrand in whatever form is convenient, say x to the power -1 over 2, and then using whatever rule we need to use in order to find the antiderivative. Now, in the case that you actually can plug in both limits, you should just go ahead and do that. Plug in x equals 1, plug in x equals 0, take the difference of those two results, and quite magically we find that the area under this curve from 1 to the vertical asymptote at 0, this result is equal to 2. Now it can happen sometimes that you are not able to actually plug in one of the limits to the function. And so I would like to show you an example of that real quick. What if we did exactly the same region of integration from 0 to 1, but we brought back our friend 1 over x squared, and we integrated that with respect to x. Now if I find an antiderivative, I will have, once again, -1 over x being evaluated from 0 to 1. But the problem here is that I can't actually plug in 0 to this function. So instead, I will use a letter a as a placeholder, and I will let a approach 0. Alright, so plugging in 1 gives me -1 over 1. Plugging in a gives me -1 over a. And if I let a approach 0, -1 over a is approaching infinity. So this quantity is undefined. And just by changing the integrand from 1 over square root x to 1 over x squared, for the same region of integration, one function gave me a finite area under the curve, but this new function has given me an infinite area under the curve. Now, we have some language that we use to distinguish the case when we get an infinite answer versus when we get a finite answer. An improper integral is said to converge, or is said to be convergent, if it has a finite value. If it has a finite value. So you are actually able to take the integral, to plug in the limits, to let one of the limits go to infinity, to minus infinity, and get an actual real number as the result. In any other case, if it is not convergent, if you cannot get a number as a result of the calculation, an improper integral is said to be divergent in this case. It's divergent if it is not convergent. So applying that language to the example from the previous page, is the integral from 0 to 1 of 1 over x squared dx convergent or divergent? Since we found that this integral from 0 to 1 of 1 over x squared dx was not a defined real number, then that means that this integral diverges. Contrast with the other two integrals that we did, integral from 0 to 1 of 1 over square root x dx, whose value is 2, this is convergent. And likewise, the integral from 1 to infinity of 1 over x squared dx, whose value is 1, this, as a result of being a real number, was also convergent. So keep an eye on this language. Once again, you will see it one more time, several more times, if you go on to take Calculus 3.